All right, let's look at our test review for sequences, exponentials, and logs. In this first set of questions, we've got several sequences, and we're supposed to determine, first of all, if it's arithmetic or geometric. If it's arithmetic, then we need to identify the common difference. For geometric, we need to identify the common ratio. And then we're asked to find the 15th term. So our first sequence, 7, 11, 15, and 19, you can see that each time to create this sequence, we're adding 4. That's our pattern here. And since I'm adding something every time, that makes this an arithmetic sequence. And my common difference here is 4. So to find that 15th term, I'm going to use the formula to find the nth term. A sub n is equal to a sub 1 plus the common difference times n minus 1. And so for us here, a sub 15 equal to the first term, 7, plus the common difference, which is 4, times 15 minus 1. And that comes out to be 63 for our 15th term. In our next sequence, 3, 6, 12, 24, you can see that we're multiplying by 2 each time to create this sequence. And since we're multiplying to create the sequence, that makes it geometric. It's a geometric sequence, and the common ratio is 2. So if I want to find my 15th term, I'm going to use the a sub n formula, which is a sub 1 times the common ratio to the n minus 1 power. So for a sub 15, it's going to be my first term 3 times the common ratio 2 raised to the 15 minus 1 power. And that comes out to be 49,152. In my next sequence, 1/2, 1/4, 1/8, 1/16, in this sequence, we're actually multiplying by 1/2 each time to get the next term. You can see that our denominator is always times 2. And again, since I'm multiplying, this is a geometric sequence. My common ratio is 1/2. And so to find that 15th term, I'm going to have the first term 1/2 times the common ratio, which again is 1/2, raised to the 15 minus 1 power. And that gives us a pretty large denominator here, 1 over 32,768. Last sequence here, 9, -1, -11, -21. It looks like here that we are subtracting 10 each time, which we are. But we're going to think about that as adding -10 each time. And so this is an arithmetic sequence. And the common difference is -10. So to find my 15th term, a sub 15 is equal to the first term, 9, plus the common difference, which is -10, times 15 minus 1. And my 15th term is -131. All right, in this next question, we're still determining whether or not the sequence is geometric or arithmetic, but then we're asked to find a sum of a certain number of terms. So my first sequence here, 3/2, 1, 2/3, 4/9. It doesn't seem to be arithmetic. We're not adding the same thing every time. It looks like it's geometric. And hopefully you can see that we're multiplying by 2/3. I think it's easiest to see in those sets of terms right there. But even in the first one, 3/2 times 2/3 would be equal to 1. So it is geometric, and our common ratio is 2/3. Now in class we talked about 2 different ways to find the sum. One way is to use the formula. My formula S sub n is equal to a sub 1, the first term, times 1 minus the common ratio to the nth power, divided by 1 minus the common ratio. And so for this sequence, we would have our first term, which is 3/2, times 1 minus 2/3 to the 30th over 1 minus 2/3. However, in class we also talked about using summation notation. And if we were to use summation notation on this one, we would be summing up the terms n equals 1 to 30. And then we're going to use the nth term formula. The first term 3/2 times the common ratio to the n minus 1 power. And remember, when you put that in your calculator, you do need to put this n minus 1. Don't substitute a number for n there if you're using the summation formula. Either formula that you choose to use here should give you the answer of 4.499. In our next sequence, 52, 47, 42, 37, we are subtracting 5 each time or adding -5. And so this is an arithmetic sequence where the common difference is -5. Now, if I'm going to use my sum formula, the sum of an arithmetic sequence is going to be equal to the number of terms divided by 2, because remember, when we're summing up an arithmetic sequence, we're really pairing up the first and last term, pairing up the second and the next to last term, and so on, and adding those pairs together. So we've got the number of terms divided by 2, and each sum is going to be equal to the first term plus the last term. And so that means in order to use this formula and to sum up the first 22 terms, I need to find the 22nd term. So a sub 22 is going to be equal to the first term, which is 52, plus the common difference, which is -5, times 22 minus 1. And that gives me -53 as my 22nd term. So I'm going to come over here and do my sum formula. The sum of 22 terms is equal to 22 divided by 2 times the first term, which is 52, plus the 22nd term, which is -53. Now you can also use summation here. We could sum up the terms, n equals 1 to 22, and we're going to use our nth term formula again for arithmetic, just like we did for geometric. It's going to be the first term, 52, plus the common difference, -5, times n minus 1. Whichever one of those formulas you use, you're going to get the answer -11. All right, question number 3. If the third term of an arithmetic sequence is 10 and the seventh term is 21, find the sum of the first 15 terms. So your test says 21, but this is a mistake on the test. We need to change that 21 actually to 22. Typo there. All right, so if my third term, a sub 3 is 10 and a sub 7 is 22. If I'm going to find the sum of the 15 terms, I need to figure out what the first term is, and I also need to know my common difference. Well, if I subtract 22 minus 10, that gives me 12, which means from the third term to the seventh term, the value of the term is increased by 12. And if I subtract 7 minus 3, that gives me 4. So that means it's taken me 4 terms to increase the value of the term by 12. And if I divide those two things, 12 divided by 4, that's going to give me a common difference, which is equal to 3. I'm adding 3 every time to get my next term. So then, since I have the third term, the first term is pretty easy to figure out. You could just count backwards, but I'm going to go ahead and use the formula to figure it out. Let me change colors here. I'm going to write the formula down. And I'm going to use this third term. It's equal to 10. A sub 1 is what we don't know. But I do know that my common difference is 3. And 10 is equal to the third term, so my n is 3. So 10 is equal to a sub 1 plus 3 times 2. 3 minus 1 is 2. 3 times 2 would be 6. A sub 1 plus 6 equals 10. And so a sub 1 is equal to 4. So now I think I have everything that I need to find the sum of the first 15 terms. Sum of 15 terms is going to be 15 divided by 2 times, oh, you know what? I don't have everything I need. I need the 15th term. So let's erase that. Let's find the 15th term. Whoops, I erased a little too much. Make that a 4. Okay. Let's find a sub 15 first. A sub 15 is going to be the first term, which is 4, plus the common difference, which is 3, times 15 minus 1, times n minus 1. And that comes out to be 46. Now I can find that sum. Sum of 15 terms is equal to 15 divided by 2, the number of terms divided by 2, times the first term plus the last term. Again, you could also use, or you could do summation, n equals 1 to 15 of the nth term formula, 4 plus 3 times n minus 1. And either way, we get a sum of 375. All right, our next question, we've got 4 bacteria placed in a petri dish. Each bacterium splits into every hour. Write a rule that shows how many bacteria are in the dish during the nth hour. Now the question here, what it's saying is that every hour, every bacteria that's in the dish goes from being 1 bacteria to splitting and becoming 2 bacteria. And so the number is doubling every hour. And so this is kind of like a geometric sequence here. I'm going to say that the population in the dish after n number of hours, whatever that is going to be equal to the first term, which is 4, the first number of bacteria, which is 4, times the common ratio, which is 2, because we're doubling the number of bacteria every hour. And 2 is going to be raised to the n minus 1 hours. All right, so the next question then says, find the number of bacteria in the dish after 9 hours. Well, if I want my population after 9 hours, that's going to be equal to 4 times 2 to the 9 minus 1 hours. And it would be 9 minus 1 because in the 9th hour, they've only had the chance to double 8 times. And so that's going to come out to be 1,024 bacteria. The next question says, if the petri dish can hold approximately 65,500 bacteria, how many hours need to pass before it is full? So for this question, we need to take our equation, which we figured out for population, the 4 times 2 to the n minus 1, and we're going to set it equal to the 65,500 bacteria. And I want to find out n, which would be the number of hours that it takes for this to be equal to 65,500. Well, if I'm going to solve this equation, it is an exponential function here on the right, and so first thing I'm going to do is divide by 4, and so I get 2 to the n minus 1 is equal to 65,500 divided by 4, which is 16,375. So now I have an exponential, and I need to undo that exponential so I can get the n out of the exponent. And so I'm going to use a log with the base of 2, since the base of my exponential is 2. So I'm going to log base 2 both sides. And of course over here on the right, the log base 2 of the 2, they undo each other, and I'm just left with n minus 1 equal to log base 2 of 16,375. And then of course to solve for n, I need to add 1 to both sides. Now when you add 1 over to the other side, it does not become 16,376. This log base 2 of 16,375, that's a term all to itself. Log base 2, 16,375 plus 1 on the outside. And then if you put that in your calculator, I get n is equal to 14.999, virtually 15 hours that it would take for the Petri dish to be full. All right, next question. The new SAT arena has 22 rows of seats in the upper level. The first row has 35 seats, the second row has 38 seats, the third row has 41 seats, and so on. How many seats are in the last row? Well, the first thing we need to decide here is what kind of sequence this is. Looks like the number of seats in each row is increasing by 3 each time. We're adding 3 seats to each row. So that makes this an arithmetic sequence. And so if I'm going to find the number of seats in the last row, which is the 22nd row, that means that I'm looking for a sub 22 in this sequence, because there's 22 rows. And I'm going to take the first term, which is 35, and I'm going to add to that the common difference, which is 3, times 22 minus 1. And that's going to give me 77 seats in the last row. Question B then, what's the total number of people who can be seated in the upper level of the arena? So this is asking me to find a sum of these 22 rows. S sub 22, that sum is going to be equal to 22 divided by 2, the number of terms divided by 2, times the first term, 35, plus the 22nd term, the last term, which is 77. And that's equal to 1,232 seats. All right, and that brings us to the end of our sequences review here. Let's talk about exponentials and logs. These first couple of questions are just making sure that you know your parent functions well. Y equals e to the x. We need to sketch a graph. When I see your graph, I want it to be crossing the y-axis right here at 1. The graph should look something like that. The domain, of course, is all reals. The range, y is greater than 0, not equal to 0, just greater than 0. This function is always increasing, and it is always concave up. It does have an asymptote. It's a horizontal asymptote at, I'm going to say horizontal asymptote, and that's at y equals 0, the x-axis, y equals 0. Now the natural log function, that's the inverse of the exponential function. And so when you sketch your graph, it's going to intersect the x-axis at 1. Should look something like this. The domain here, x has to be greater than 0, and the range is all reals. Notice that the domain and range switch for these two functions because they are inverses of each other. And with inverses, you switch the x's and y's. This function is always increasing, but the natural log function is concave down. And for asymptotes, there's no horizontal asymptotes, but we do have a vertical asymptote here, and that's at x equals 0, which of course is the y-axis. All right, in this next section, we're looking to see if you can apply those log properties, if you know the log properties. We've got a log expression here, and we want to expand it. So I see here that these terms, the 8a and the b, they're being divided. And whenever I'm dividing inside a log, I can separate them and turn it into subtraction, because if I'm dividing, I subtract exponents, and logs are exponents. I'm also multiplying with the 8 and the a. Those are being multiplied. And so I can expand that and turn it into addition, because whenever you multiply, you add exponents. So log base 5 of 8 plus log base 5 of a, because those were being multiplied, But now I'm going to say minus log base 5 of b, because b is being divided. Let's look at the next one. I've got natural log of g squared divided by h to the 5th. Again, I'm dividing here, and so I can expand this to be natural log of g squared minus the natural log of h to the 5th. But one more thing that I can do here to expand this is these exponents, the 2 and the 5, those can be moved into the front to be multiplied by the log. And so my final answer here would be 2 times the natural log of g minus 5 times the natural log of h. Now in this next section, we're kind of doing the opposite. We're taking an expanded log and we're condensing it down to just a single log expression. So I notice here my first two logs here, they're being added together. And so that means when I condense them, I'm going to multiply, because whenever you're adding exponents, that means that you're multiplying. I've also got this 3 here that I can rewrite as an exponent on b. Same thing with the 4. I can rewrite that as an exponent on the c. And the c, the log of c is being subtracted. And so, of course, that means that when we condense it, we're going to divide that c. So my condensed version should look like this. Log of the 4th root of a times b cubed. So I may put that 3 as an exponent on the b. I multiplied here because previously we were adding the logs. We were adding the exponents. And next it says minus, so I'm going to divide c to the 4th. All right, in question number 10, natural log of j divided by 3 plus natural log of k divided by 3 plus the natural log of m divided by 3. It might be easier to picture what to do on this question if we look at this as 1/3 times natural log of j plus 1/3 times the natural log of k plus 1/3 times the natural log of m. And so now I've got that, instead of dividing by 3, I'm writing it as a fraction in the front, and this fraction 1/3 can become an exponent on j, and likewise on k and on m. But remember, whenever we have a fraction exponent, we can rewrite that as a root. Fraction exponents can be rewritten as roots, and so my final answer here is going to be the natural log of the cube root, and then notice all these logs are being added together, and so I'm going to multiply j times k times m. And I put them all under the cube root because they all have that 1/3 in the front, which becomes an exponent on the variables and can be rewritten as the cube root. All right, in this next section, we're going to start solving some equations. This first example here, first problem, we want to solve by rewriting with like bases. So here I've got a base of 4 and a base of 64, and I want to change those to be the same base. Well, hopefully we notice that 64 can be rewritten as 4 to the 3rd. And so I'm going to keep my base of 4 on this side, but I'm going to rewrite 64 as 4 to the 3rd, and then of course times that 2x minus 2. Now that my bases are the same, that means that my exponents must be equal to each other. And so 3x plus 5 is equal to 6x minus 6. And then we can solve for x. I'm going to subtract the 3x over to this side and add the 6 to the other side. So I got 3x equals 11, and divide by 3 to get x equals 11/3 as a final answer. Now in this one, we've got 1 over 216 is equal to 6 to the 5x minus 8. 216 can be rewritten as 6 to the 3rd, but notice that that's in the denominator of a fraction, and so really I need to rewrite this whole side as 6 to the negative 3. I can write it with a negative exponent because it's in the denominator. and that would be equal to 6 to the 5x minus 8. And so now that I have like bases, my exponents must be equal to each other. And 5x is equal to 5 if I add 8 to both sides, and then I divide by 5, and x is equal to 1. Now in these last equations, we're just solving the equation. Notice here I've got an exponential equation, so I'm going to get that exponential term by itself by adding 8 to the other side. So 15 to the 3x is equal to 18. And now to undo the exponential, I'm going to use a log. I'm going to log base 15 both sides. And the log base 15 of 15, those undo each other, and I just get 3x equal to log base 15 of 18. And finally, my last step, I'm going to divide by 3. So x is equal to log base 15 of 18, all divided by 3. And I'm going to leave that answer right there in that form. When you do these questions on the test, you will not have a calculator, and so this form that I've stopped here, this form is the answer, the type of answer that I'm going to be looking for. On question 14, this time I've got a log equation. So I need to get this log expression by itself. I'm going to start off by subtracting 2 from both sides. So now that's equal to 3. Next step, I'm going to divide by 3 on both sides to get rid of that 3 in the front. And I get natural log of 4x minus 1 is equal to 1. So now to undo the log, I'm going to make both sides exponents. And I'm going to choose e as my base because natural log has the base of e. So e to the natural log of 4x minus 1 equals e to the 1. The e and the natural log undo each other, and I'm left with 4x minus 1 equals e to the 1. And now all I need to do is solve for x. I'm going to add 1 to both sides, and then finally divide by 4. So e plus 1 divided by 4 is our final answer. Number 15, got another exponential equation. So I need to get this exponential term by itself. I'm going to divide both sides. I'm sorry, not divide. I'm going to subtract 15 from both sides. And I get negative 2e to the 4x is equal to negative 3. Then now I'm going to divide by negative 2. And I get e to the 4x is equal to negative 3 divided by negative 2, which would turn into positive 3/2. And now I need to undo the exponential, and so I'm going to use a log. And since it's a base of e, I'm going to use the natural log of e to the 4x. And I'm going to natural log both sides. The natural log and e undo each other, and I'm left with 4x is equal to the natural log of 3/2. And my last step here to solve for x would be to divide by 4. X is equal to the natural log of 3/2 divided by 4. All right, question 16. I've got a log equation here, but there's 2 logs, and I need to combine those together before I can solve this equation. So I'm going to use my log properties. Whenever I'm adding logs, I know I can condense that to 1 log if I multiply 4 times 3x minus 5. Because whenever you're adding exponents, that means you're multiplying. And now I've got the log expression. It's combined and it's by itself. So I'm ready to undo the log. I'm going to make both sides of my equation an exponent on a base of 5 because the base of my log is 5. So 5 to the log base 5 of 4 times 3x minus 5 power is equal to 5 to the 7th. And 5 to the log 5 power, those undo each other. And I'm left with the 4 times 3x minus 5. I'm going to go ahead and distribute. I need to distribute that 4. So 12x minus 20 is equal to 5 to the 7th, and I don't know what that is without a calculator. So I'm just going to leave it 5 to the 7th. We're going to add 20 to both sides. 5 to the 7th plus 20. And in the last step, divide by 12. 5 to the 7th plus 20 over 12. And that's my final answer. Question 17. I've got an exponential. Need to get this exponential by itself. First thing I'm going to do is subtract 7 from both sides. So 5e to the 2x minus 1 over 3 is equal to 8. I subtract 7. Now I need to get rid of this 5/3. And so I'm going to multiply both sides by 3/5. And e to the 2x minus 1 is equal to 24/5. And now I'm ready to undo the exponential. So I'm going to use a natural log. Natural log and e undo each other. And I'm left with 2x minus 1 is equal to the natural log of 24 over 5. I'm going to add 1 to both sides. And final step, divide by 2. And so x would be equal to the natural log of 24 over 5 plus 1, all divided by 2. All right, next question. I am saying skip this question. I worked it out earlier, and there's a mistake somewhere, and I can't figure out where it is. So we're just going to skip this one for now. If I figure it out, we'll talk about it in class. Let's look at the last section. So it's just rewriting these expressions using our exponent properties. So in this first one, I've got a cube root here. And remember, whenever we have a root, we can rewrite that as a fraction exponent. And so instead of cube root of x squared, we're going to have x to the 2/3 power. Cube root becomes a 1/3. Now the y cubed is in the denominator, and so I can rewrite that as y to the -3. And that would be my final answer. In this next one, I've got the square root of 3x squared. And so that square root, I'm going to rewrite it as a fraction, 1/2. Again, I've got y cubed in the denominator, and so I'm going to rewrite that as y to the -3. Now in these next two, these are written with negative and fraction exponents, and we want to go back the other way. So we're kind of working backwards from how we were doing in 19 and 20. And on 21, a little bit tricky here. Notice that this -3 exponent, it's only for the a. A lot of students would take the 5, keep the 5 with that a, but the -3 is only for the a. The 5 is going to stay here, but since the a has a negative exponent, I'm going to move it to the denominator and make it a cubed. Now the b has a positive exponent, so it's going to stay in the numerator, but that exponent is a fraction. And so that means I need to turn it into a root, and it's going to be a cube root of b to the 5th. Finally, this 2x has a negative exponent, so I'm going to write 2x in the denominator because of that negative exponent. It also has a fraction exponent, and so I'm going to turn that fraction exponent into a root, and it's a square root, so I don't have to put a little number there, but that 3 is going to stay as an exponent on the 2x, just like that. Now the 5y cubed, those all have positive exponents. They just stay in the numerator, and so my final answer looks like that.